In addition to benzene and compounds closely related to benzene, we want to find out whether we can identify aromaticity in other compounds. Being aromatic means that there is a special stability of an aromatic compound because of delocalization of electrons. Special stability because of delocalization of electrons. How do we determine whether a compound is aromatic? This can be done experimentally based on its energy and structure. So then how do we identify aromatic compounds? Well, so far we've seen compounds that are like benzene. So it could be benzene itself, it could be substituted benzene, or it could be fused benzene rings. But is there a more general definition? Well, let's try to think about what this could look like. What do we know about benzene? It is planar, it is cyclic, and it is fully conjugated. So is this a sufficient definition to identify other aromatic compounds? Let's take a look. Let's recap how we determined aromaticity for benzene. One approach is based on energy. So if we think about the heat of hydrogenation for cyclohexene reacting with hydrogen to give cyclohexane, this has a delta H of negative 120 kilojoules per mole. So if we look at this on an energy diagram, then if this is the energy of cyclohexene, then this is the energy of cyclohexane, and so this difference is 120. So let's think about this going all the way across, because hydrogenation of any of these compounds will lead to the same product of cyclohexane. If this cyclohexadiene is just a hypothetical non-interacting diene, then we would expect that the hydrogenation would be just twice the hydrogenation of this. So we would expect that this would be 240. And if this is a hypothetical non-interacting cyclohexatriene, we would expect that this energy would be 3 times the original, so 360 kilojoules per mole. But experimentally, it's been shown that for the cyclohexadiene, the heat of hydrogenation is 231 kilojoules per mole. So it is 9 kilojoules per mole more stable than the hypothetical non-interacting diene. So this means that this conjugated diene is stabilized by 9 kilojoules per mole. So this is its resonance energy. If we look at benzene compared to the hypothetical non-interacting cyclohexatriene, benzene has a heat of hydrogenation of only 208 kilojoules per mole. That is 152 kilojoules per mole more stable than expected. So here we have a ton of resonance energy, right? So it's not just being conjugated, but there's something even more special than that because it has 152 kilojoules per mole of resonance energy. That's what it means to be aromatic. Another way that aromaticity can be determined experimentally is to focus on structure. So first of all, let's think about bond length. If we consider 1,3-butadiene, well, this has a bond length of 134 picometers and 146 picometers. So if benzene was similar to butadiene, then we would expect that this would have a bond length of about 134 and 146. So this would be the expectation. But experimentally, it's shown that benzene has bond lengths of 140 picometers. So it does not exist as alternating double bond, single bond, double bond, single bond, because then we would have different bond lengths. Instead, experimentally, it's shown that every single benzene bond is 140 picometers. So rather than thinking of it as the alternating single bond, double bond, we know that we have delocalized electrons, and we can think of it as being like a 1.5 bond. Another feature to consider is planarity. So experimentally, benzene has also been shown to be completely planar. Right? Now this is important because it allows for effective overlap of p orbitals to give a delocalized pi system. Benzene is completely flat, then that means all of these p orbitals are going to be exactly perpendicular, which means parallel to each other, so that we have very good overlap. If there was a pucker, then you'd have a p orbital this way, one this way, and this way, and so the orbital overlap wouldn't be as good. So the fact that benzene is planar gives us that possibility of the effective p orbital overlap to create a delocalized pi system. So for benzene, both energy and structure were used to explain aromaticity. So if we look at other cyclic, fully conjugated polyenes, can we use energy and structure to identify other aromatic compounds? So compared to benzene, let's go to the next largest cyclic polyene that is fully conjugated, and that would be cyclooctatetraene. So if we compare cyclooctene, the heat of hydrogenation is -96. So here is our final product, cyclooctene. We have an energy difference of 96. So if we had a hypothetical non-interacting cyclooctatetraene, then we would expect that this heat of hydrogenation would be 4 times the heat of hydrogenation of cyclooctene. And so we would expect that this would have a heat of hydrogenation of 384 kilojoules per mole. Experimentally, it's shown that the heat of hydrogenation is actually 410. It is higher in energy than the hypothetical isolated alkene. All right, so based on energy, this clearly is not aromatic. What about based on structure? Well, experimentally, the bond lengths in cyclooctatetraene have been shown to differ. So there are some bonds that are 146 picometers and some that are 133 picometers. So clearly this is not a nice even 1.5 bond. There is a difference between the bonds. And finally, it's been shown that the shape of cyclooctatetraene has kind of a cup shape to it. So these p orbitals and these p orbitals are not going to overlap very well because they're not parallel to each other. So, is cyclooctatetraene aromatic? Based on energy? Nope. Based on structure? No. So, even though it is a cyclic, fully conjugated polyene, that's not sufficient to be aromatic. Let's apply this approach to a compound that's smaller than benzene, and let's look at cyclobutadiene. So the heat of hydrogenation of cyclobutene is -120. So here's the energy of our product. This must be the energy of cyclobutene, and our difference in energy is 120. If this is a hypothetical non-interacting diene, we would expect that the heat of hydrogenation would be twice that of cyclobutene, so we would expect a heat of hydrogenation of 240, which would give us the energy of our compound up here. But experimentally, it's shown that the heat of hydrogenation is actually 390 kilojoules per mole. So because the heat of hydrogenation is so much bigger, what this tells us is that the energy of this compound is actually much higher than what we would expect, right? So it's not specially stabilized by aromaticity, it's actually destabilized compared to what we would expect. Now, in terms of structure, it's been shown that cyclobutadiene has bond lengths of 135 picometers and 156 picometers. So this is much larger than the typical carbon-carbon bond. So cyclobutadiene really takes on kind of this elongated shape. Is cyclobutadiene aromatic? Based on energy? Nope. Based on structure? Nope. So the characteristics of benzene, being cyclic and fully conjugated polyene, this is not a sufficient definition to identify an aromatic compound. So there's got to be a different way to identify it. So being aromatic means that a compound has a special stability. All right, so a compound is particularly stabilized by delocalization of electrons in a ring. Well, we can also define anti-aromaticity, and this is a special instability so that a compound is particularly destabilized by the delocalization of electrons. Cyclooctatetraene and cyclobutadiene, they would be anti-aromatic if the electrons were delocalized. So the molecule actually adopts a different structure to minimize the delocalization. If cyclobutadiene was a perfect square, which I can't draw, then there would be significant overlap of the p orbitals leading to delocalization of electrons. So instead, cyclobutadiene has a very elongated shape to minimize the orbital overlap of the different p orbitals. In cyclooctatetraene, the molecule takes on a significant cup shape so that the p orbitals are not parallel to each other, because this molecule would be destabilized by the delocalization of electrons. Earlier, we proposed a general definition for an aromatic compound is that it would be a cyclic, fully conjugated polyene. Well, apparently this is required because that's what benzene has, but it's not a sufficient definition because this describes cyclobutadiene and cyclooctatetraene, but those compounds are not aromatic. So there's got to be something more. So to add to our characteristics of an aromatic compound, we can use Huckel's rule. So among planar, monocyclic, fully conjugated polyenes, those with 4n plus 2 pi electrons will be aromatic. Those with 4n pi electrons will be anti-aromatic. Benzene has 6 pi electrons. So one way to think about this is if n equals 1, then 4 times 1 is 4 plus 2 equals 6, and that's what we have here. So this solves the 4n plus 2 pi electrons, so this is aromatic. Another way you could think about this is if we have 4n plus 2 and we want to find out if that's equal to 6, 4n equals 4. If we subtract 2 from both sides, n equals 1, we get a whole number. Therefore, benzene is aromatic. If we tested it with the anti-aromatic rule, then we would say is 4n equal to the number of electrons in benzene? Well, nope, because n would be 6/4, which does not give us a whole number. What about cyclooctatetraene? This has 8 pi electrons. So if we tried to set this equal to 4n plus 2, is that equal to 8? 4n equals 6, and so we do not get a whole number for n. So cyclooctatetraene does not fit with 4n plus 2, so we know it is not aromatic. Going in the other direction then, if we tried 4n n, is that equal to 8? We can solve for n equals 2. So because this has 4n pi electrons, then cyclooctatetraene would be anti-aromatic if it was planar. Right? It would be anti-aromatic if it had delocalized electrons. So it adopts a different shape in order to avoid that special instability, right? It's still higher energy than expected. So it's already destabilized because of the fact that it's adopting an odd structure, right? So it would be even more destabilized if it was planar and anti-aromatic. Finally, let's take a look at cyclobutadiene. This has 4 pi electrons, and so obviously this is going to fit with 4n, where n equals 1. So because the 4 pi electrons, that fits with the 4n pi electrons, then this compound would also be anti-aromatic. So rather than being anti-aromatic, they will adopt a structure to minimize that delocalization. All right, so Huckel's rule is a helpful way to try to identify whether a compound can be aromatic or not. Notice this includes monocyclic in the definition. So other compounds can be aromatic, bicyclic, tricyclic compounds can be aromatic. It's just that you can only use Huckel's rule if you're talking about a monocyclic compound. Now, another way that we could try to identify or explain aromatic compounds is by using molecular orbital theory. Remember, we're talking about the linear combination of atomic orbitals to give us molecular orbitals. We can treat the pi system separately from the sigma system. With benzene, then, we're just looking at the p orbitals. Now, when we were just looking at the Diels-Alder reaction and we were thinking about butadiene compared to ethylene, it was pretty easy to think about the possibilities of the p orbitals phase up, phase down, but it's actually harder to do that with benzene because, for example, here we've got this molecular orbital results if everything on top is one phase and everything on the bottom is the opposite phase. Here, if we've got blue on top and then here red on top, then that gives us this molecular orbital. Here we have this carbon is half blue, half red, so it's harder to determine the molecular orbitals, right? We can't just do this by guessing, we have to compute it, all right? But what do we get? Our molecular orbitals in benzene, we have a pi 1, we have pi 2 and pi 3 that are equal energy to each other, and then we have a pi star 4 and 5. These are higher energy, these are antibonding orbitals, and then we have a pi star 6. This one is the highest energy. Because we have 6 pi electrons, we fill in the electrons starting at the bottom, so we have 2, 4, 6. These are all in bonding orbitals. So benzene is very stable because all of the pi electrons are in the bonding molecular orbitals. So we can just apply molecular orbital theory to cyclobutadiene and cyclooctatetraene and any other compound that we want to look at. But that's difficult to do. Luckily, there is a shortcut. So a shortcut that we can use with molecular orbital theory is to use Frost's circle. So if we just want to be kind of qualitative, not quantitative, then to determine the relative energies of the molecular orbitals, Frost showed that if you take your compound and start it out point down and inscribe it in a circle, so let's pretend this is a nice even circle, then this gives you the energy levels. So this would be the first molecular orbital, and then we have 2 higher energy but equal to each other, and then 2 more higher energy equal to each other, and then 1 more at the highest. We are looking at here and here, and here, and here. We have 6 pi electrons, so those get filled in 1, 2, 3, 4, 5, 6. So these are all in bonding orbitals. So we can do the same thing with cyclooctatetraene. We don't have to put it in the circle, but we do have to write it point down. So this is our lowest energy molecular orbital. Then we're going to have 2 more that are higher energy equal to each other, 2 more, 2 more, and then 1 more. Now here we have 2, 4, 6, 8 pi electrons. So we fill in 1, 2, 3, 4, 5, 6, and then 7, 8. So we have some electrons in bonding orbitals, but we have, first of all, unpaired electrons. That's not stable. And this would be in a non-bonding orbital. And so there's no real advantage to having a delocalized pi system in this case. Let's do the same thing for cyclobutadiene, and our molecular orbital picture would look like this. We have 1 orbital here, and then 2 molecular orbitals, and then 1 more molecular orbital. And if we fill in our electrons, we have 4 pi electrons, right? 2, 4. So 1, 2, 3, 4. Right? Again, these are bonding orbitals, these are anti-bonding orbitals, and these are non-bonding molecular orbitals. So sure, we have 2 electrons in a bonding molecular orbital, but then we have 2 electrons in a non-bonding orbital, so there's no advantage, and they're unpaired, so that is a disadvantage. So having a delocalized pi system that leads to this molecular orbital picture, it's not an advantage overall. We have the shortcut to look at the molecular orbitals that would result from a particular compound. When we fill in those electrons, we can see whether there is an advantage to having the delocalized system that leads to this set of molecular orbitals, or if there is no advantage to having this delocalized system of molecular orbitals, these bonds will be isolated. They will act like they are isolated rather than having the electrons delocalized.